Welcome to a discussion with Florian Achermann regarding his paper Watching the Air Rise, Learning-Based Single-Frame Schlieren Detection. What we are interested in this paper is to identify particular patches of air that have some kind of disturbance or temperature gradient. We're going to do that with the help of, or rather Florian has done that with the help of camera technology and CNNs. I hope you enjoy it. It would be interesting, I think, to give some background why you chose to study this topic in particular. Like, why this specific area? Is it some affiliation with the part of the university that you were in, or what is the background?
Yeah, so my background is that I worked with UAVs, and specifically I researched on how can you make these UAVs fly a bit more efficient in, for example, the Swiss Alps or in alpine environments in general, and also safer. So for safety and efficiency, one part that I did as my research was predicting the wind. And then kind of as a side project, at some point we started, okay, so you can also exploit thermal updrafts, which are kind of this hot rising air that is going up. You can exploit these as well with UAVs. So we started side projects on this side. And at some point we thought, okay, so I think you remember, so if you look, for example, on a very hot day on a street, you can kind of see this shimmering. And so we thought kind of it would be really cool if we could visualize this shimmering as well, because that could help us to detect potential thermal updrafts. And we started looking into that, if it would be even possible. And then we found kind of some classical methods that could do it, but they wouldn't be suited really for using using it on board on our plane. And then we started kind of this work here, where we tried to really detect this kind of shimmering or this Schlieren, how they're called, from a plane. And so this was kind of over some edges, we came towards that topic, and yeah, we were lucky to make it work. I mean, when we started all of this, it was really as a side project. And initially we thought kind of, okay, so it's not really possible. We didn't think it would work out at all. And then we started kind of making baby steps towards kind of the goal, and it always worked. And then we were always a bit surprised, and the better it worked, the more surprised we were in the end. So,
okay.
Yeah.
Okay, so when we're talking about the shimmering, so if I guess you're saying, like, if you're looking at the street, let's say on a hot day, you can see that just above you usually have this kind of, flickering or whatever in the air. Is that purely a temperature dependent thing, or I'm thinking if you're trying to take this and you're trying to apply it to the setting of a UAV that's somewhere high up in the air, are there other factors that, of course there are other factors, but that same kind of behavior, would you even observe it if you had similar temperature situations?
So, I mean, in the end, so, I mean, this is due to Snell's law. So if you have kind of light passing through media, which has different densities, there will be some refraction of the light rays. And this is kind of, that's the reason we have this shimmering. And so one reason is kind of, yes, if you have temperature gradients in air, you will have this small refraction, just because there you have small bubbles, or you have kind of this very localized temperature gradients and sharp ones. So that's why you can actually observe them by eye. However, I mean, this is still a bit an open question. So this work here is an indoor lab setting, and outdoors, as we will maybe later show, I mean, it doesn't work yet. So it still remains a bit open whether, for example, the actual thermals we would observe kind of are causing strong enough, let's say, reflections that we can actually observe with such a camera. Maybe one, let's say, solution to this could be we use higher resolution cameras on board. I mean, the one that we used in our work here is a pretty standard one with, I think, HD resolution. So it's nothing really special. So if you use more specialized cameras, you could maybe potentially see them a bit further away, or even detect smaller refractions. There's also one other, let's say, limitation to this work is that, I mean, it works best, or the refractions are the greatest, if kind of the heat source or kind of the dense or these gradients in the air are spatially closer towards the camera. So if you would be flying, you would get a strong response if the thermal is already closer to you than closer to the background. So I think technically speaking, so if you would fly around, so you were more likely to detect closer thermal updrafts with this work. But it would not only be limited, for example, to thermal updrafts. So one other, let's say, area where you could use this work is, for example, for leak detection. So it's because if you have, for example, a gas pipeline or something else with a different, let's say, gas that has a different density than air, or for example, it might be higher pressurized. So if you have kind of a leak there where it would go out, you could also potentially see it with this work. So we also did some initial tests, for example, just with some pressurized air, and you can see it not as well as the high temperature gradients, but it's also visible due to this effect of the refractions here.
Okay. We're getting ahead of ourselves a little bit,
Yeah.
but since we're talking about that already, I would want to jump in and ask if you're considering gas leaks, for example, would you be able to use these BOS techniques, for example, that you're outlining in the paper right now already? Because my understanding with the ambition of this paper is you want some approach to analyze these air currents or air temperature gradients in situations where the vehicle where this camera is mounted is moving. That's the critical aspect of this.
Yes.
And if you're considering gas leaks, for example, there are already more or less established techniques, at least as far as I understand, for detecting that. Do you agree? And are there applications where, like, you anyway would want to use an approach like this for something like gas leaks?
I mean, yes. So, I mean, there are obviously solutions that detect. So, I mean, there are also sensors that are kind of sensing if there's a leak or not. I mean, BOS techniques would also be applicable if you have kind of, let's say, if you have a high texture background and a static camera. So, I mean, this is really usually you need a high resolution or very good camera. It needs to be static. So if it moves even a little bit, then your kind of approach or the output will be not usable. I mean, this is actually also one challenge that we had during data recording. We really had to make sure that the camera does not move, even if one of us bumped the table a little bit. That recording was unusable. So, I mean, if you have this setup, you could use it for one location. One advantage of this method, for example, could be that you could mount it as well on a drone. And for example, for these long outdoor pipelines that are hundreds of kilometers, you could just fly over it and then very easily detect where this is, because it also works with natural background, because it trained it with these kind of quite random backgrounds. So it's not really fixed to a high texture background that usually these BOS methods require.
Oh, okay. So let's maybe talk about the setup for this. We have this introductory picture on the screen, and I think that would be a pretty good thing to look at. So we mentioned BOS techniques, and those are existing techniques that work in a static environment, so to speak. And what we were talking about was putting this on a UAV or some moving obstacle and still sensing the same thing. First of all, if you have a situation like this right now, what is currently being done to assess both air currents, but then also air temperature gradients, if these are the two most promising quantities? Yeah.
So, I mean, for, let's say, the currents or the wind in general, what UAVs at the moment do is they sense the local wind. So using GPS and airflow sensors, you can get a local estimate of the wind. And then generally what they do is most of the time they just assume that the wind is locally, let's say, constant. So we have a constant wind field. I mean, some larger, let's say, or if you fly a bit further away, so beyond visual line of sight, so you have missions that span hundreds or tens of kilometers, you might want to use the weather forecasts. However, there's one, let's say, issue that usually these forecasts are too low resolution. So that's also what we noticed. For example, in Switzerland, we actually have very high resolution weather forecasts in the order of kilometer, but also the terrain is, for example, approximated at this kilometer scale. And that was one line of work that I did is, can we kind of downscale weather predictions or have a high resolution local wind field estimation using our onboard sensing and the known topography. So this is kind of the line of work that for UAV works in terms of, let's say, the wind flow, so the static wind flow that is terrain induced. If you're talking about these currents that are, let's say, these thermals, that is kind of thermal induced updrafts. I mean, currently UAVs just fly around and hope to stumble upon one. So there's no targeted search or at least for UAVs, there's no clues implemented where they could be. Right. I mean, there exists some work that, for example, based on history. So if you fly around, based on history. So if you've once observed the thermal at a certain location, you might want to fly back because there's just a higher correlation again that you can fly there. There is some other work that, for example, observes clouds. So above large thermal updrafts, there are certain clouds forming with certain shapes. So if you can detect those, for example, with a camera, you could also potentially detect thermal updrafts. I mean, there are also other clues. For example, human glider pilots, they look at the texture of the ground, and based on their experience or based on, for example, how the wind, based on the wind direction, I mean, they can infer sometimes where there is a high likelihood of thermals. But this work is still remaining to be kind of implemented for UAVs, that we can, or at least being implemented and shown in flight that they work. There has been a lot of theoretical work, but very few actual thermal soaring work shown in the real world here.
Do you know, maybe this is a silly tangent, but do you know if there are established theories on what birds do, if they're leveraging this in some way? Like whether they're able to use some, like if they're able to predict this in some way, because I guess they're in a similar situation where they're looking to save resources, and if evolution had a good way to get around it, I'm sure they're taking it into account in some way.
I mean, I have I don't really know how birds do it. So what I guess is, because of their feathers, I think they can much better sense kind of the airflows around them. And so, for example, if they sense on the right wing some updrafts, maybe they tilt towards it. So this is also, for example, how UAVs can detect it. So if you have a roll moment, or if you sense that there's a roll moment on your plane, you want to bank in towards that direction, because then in that direction you most likely have some updrafts if you want to exploit them. So this might be one thing. What I think also happens is usually there's not a single bird around, so there are a lot of birds around, so they can scan the sky quite quickly. And then I think there's kind of this group behavior or social behavior. So if they see one bird flying up and kind of, or let's say soaring upwards, then they join that. Because also during our test flights, or not test flights for this project, but other projects, sometimes we tested our planes and we flew around in circles. What we observed is that at some point a bird would join us, kind of fly some circle as well, until it realizes that there's no updraft, and then they would go somewhere differently. And then sometimes what we observe, there's one bird, let's say soaring, so having or catching a thermal, so flying upwards, and then at some point other birds will join as well. So I think there's really also, I mean, this group behavior, which you could also leverage on a drone. So for example, if you had a very good bird detector on a camera, and then you could see kind of birds flying upwards without flapping their wings, this could be another clue to remotely predict these thermals. So this is really the goal of this work, that we would not rely on chance anymore to randomly stumble upon a thermal, such that we could guide the search a bit more and thus make thermal soaring a bit more reliable for UAV drones.
Okay, it's a very interesting use case. Let me maybe switch the conversation then to the solution that you're actually looking to implement. So on a high level, you're looking to take a CNN and make that your guiding light, let's say, for detecting these. My question is, why, to begin with, do you think that's an approach that could be taken? So there's a question of how much is hardware restricted here, and how much is just a matter of having a smart algorithm to deal with it. And we seem to be saying that at least we think the hardware in a situation like a moving UAV with looking at the surroundings is good enough to pick up necessary signals to detect updrafts. Is that evident to you, or is that also a big question mark?
That would still be a big question mark, because I mean, this algorithm so far, we haven't really been able to test it on a UAV, because it with natural backgrounds and natural lighting, it still doesn't work. So it still kind of remains to be seen if this works outdoors. I mean, this is kind of really the first step towards this, where we wanted to explore if it would be even possible. Because, I mean, there, as you pointed out already, there exist already a few methods with a very sophisticated setup that allows you to detect these small refractions, the BOS method. So if you know the background, it works. There has been also work outdoors actually with 2 cameras to capture the Schlieren effects of, I think, or the tip vortices of a helicopter. So, I mean, these methods for sure, they work outdoors if you have, let's say, big enough density gradients in the air. So, I mean, so if you have kind of a strong enough thermal updraft, or if you have strong enough density gradients, it would also work outdoors. The question that we're still also a bit unsure is whether thermal updraft, which would result in strong enough density gradients up in the air. So this is also really something we don't really know, because we don't really know how hot the air will be. Will it be, for example, humid? What is the effect there on these refractions? So these are still some open questions that we don't know let's say the solution yet, or the answer yet. Yeah.
Mm-hmm. How big of a role does the background have with existing techniques in a situation like that? Like, would you be also dependent on having a high texture background?
No. Existing methods, how they work is you take a snapshot of the background without the distortion in place. So you would need the background without the thermal, which let's just assume we could obtain that. And then you need to record exactly the same viewpoint as well, now with the thermal. And then kind of they do then you apply optical flow methods, which then try to infer how each pixel in the image moved. And then you get out kind of this flow picture. And I think what you're relying on is that you have, let's say, enough texture such that you can detect these kind of pixel movements. And the real challenge is that, at least in our datasets, or when we recorded these flows with our setup, I mean, these were flows in the order of a pixel. So this is really, so you need really, let's say, a high texture background. So for example, if you had just a regular wall, it wouldn't work. So there wouldn't be enough texture. So I think also if you just applied with a standard camera, these BOS methods, then you need a high texture background. So there's one solution to this. You could just use a very high resolution camera, because then even natural background would have enough texture. So there is kind of these 2 solutions to it. But then at some point, for example, if we talk about small drones, we couldn't really carry kind of a 2 or 3 kilogram camera just for this purpose. At least for our small scale drones, that wouldn't be possible.
Yeah. When we're saying that it's in the order of magnitude of 1 pixel, are we talking about the distortions between the 2 pictures then, if you compare them, or what is it that we mean exactly? Okay.
Yes. Yeah. So it's kind of, if you talk about the 2 pictures, so the difference is kind of that these pixels moved in between the 2 recordings, or kind of you have pixel movements, or movements in the image with less than a pixel, or in the order of a pixel,
Right. Okay, interesting. So let's talk a little bit about architecture then. So you're using, I believe it was UNet or something like that, as an architecture. I actually have a link to the paper as well, so we can quickly look at the corresponding image. It would be this one, that I guess you're using kind of the architecture. Would you mind just running down, roughly speaking, what kind of architecture you're using to do this prediction, and also what the expected input/outputs of the system would be?
Yep. So the input would be a single image, or that we recorded. So 1 frame, for example, of a video that you might see later on. And then the output, in this case here, would be 2 channels, would be kind of the flow direction in the X and Y direction, so in pixels. So that is kind of the input and output. And what the network does, it uses the input image, then it applies some convolutions, and then it does this and then it also leverages downscaling, so reducing the reducing the size of the image while increasing the dimensionality in terms of channel. So you can encode more information per pixel at a lower resolution, and then it applies a certain kind of number of blocks of this downscaling, and then it has some encoding of the image in the end, and then it kind of does the reverse. So getting from a lot of information per pixel from this encoding, and encoding that into the other information that hopefully then results in an output picture or an output flow prediction that has the same dimension as the input image.
Mm-hmm.
Yeah, and this is
And
kind
you
of,
made, sorry,
I mean, it's already
go
a
ahead.
pretty standard, or it's already a bit of an outdated network structure in terms of, I mean, there would be, for example, more powerful structures such as transformers, but we on purpose chose this because it's kind of quite a simplistic network that has been already been applied to quite a few different approaches, and it's also quite or relatively fast to train and quite easy to train. So for transformers, there are quite a few, let's say, nitpicks, or there are more ways it could go wrong. So we wanted to kind of eliminate one of these factors of complexity. So we wanted to really try a network that has minimum complexity that still might work in the end. So I think also if someone else wanted to pick up this work, I mean, there would be definitely other network architectures that could potentially result in much better predictions. But we really wanted to go with kind of a minimum complexity approach to see if it would work at all.
Mm-hmm.
Yeah.
Okay. And you made some small modifications from this architecture in the actual application that you did. Are any of those worth highlighting, or what was the reason for deviating slightly?
Maybe I think I think this is also fully convolutional. So, I mean, what we do is kind of, there are some variants that have at the bottleneck, they can see really at the bottom of the unit. Some of them apply, for example, let's say linear layers there, and then you're bound to kind of the input image size. And our network is really fully convolutional. So that allowed us to, for example, train the image or the network on smaller images to make the training a bit more efficient. But then, for example, deploy the network on the full resolution image or videos that we recorded in the end. So, but other than that, I mean, it's pretty much the same as you can see here in the picture.
Mm-hmm. Okay, very good. So let's go back to the paper, and then we can talk about the approach. So we have this network, and how do you actually get it to work now if we talk about training and all this stuff?
Yep. I mean, the first step for any data-driven approach was kind of, maybe if we can go to this image here, was the data recording. So we had to get kind of the data to train the network. And there we leveraged kind of these traditional BOS methods. And we used our camera that we could also carry on board of our plane. It's a really lightweight camera with a standard resolution. We also tried different backgrounds. So on the right-hand side, you can see, I mean, in this image, you can't see much, but it is kind of a sinusoidal pattern. And we also tried checkerboard pattern, Perlin noise, or other patterns. And then you record a video in this scene. And in the middle, you have a heat source. So here we had just a heat plate. We also had a smaller heat plate that resulted in slightly different motion or flow patterns. We also set the heat plate to different temperatures, which also resulted a bit the different flow patterns. And then we just recorded a bunch of data. So I think we had around 100 different setups where we moved the heat plate around. So we wanted to really also capture different flow patterns, because in the end, the network will learn what is happening in the data set. And if we have a kind of a too unique, or if we don't have enough kind of different examples of flow, it will just overfit to some of these examples. Mm-hmm. And so we also tested then different optical flow methods to record kind of these background-oriented Schlieren methods. So on the right-hand side here, just a bit, you can see the different methods. So we tested Honchunk, Lucas Canada, which are all methods kind of to detect between 2 pixels. How was the motion between, or what is the motion between the 2 pictures? And in the end, Honchunk worked best for us. And then we kind of ran through all the data that we have with the Honchunk method to detect these optical flows. And
is there a reason?
Sorry?
Is there a conceptual reason why you think Honchuk worked better than the other candidates?
I mean, one reason is that Honchunk does some smoothing over, let's say, over a certain region. So there's a factor that you can set, or that we tune a bit to get the best results. Because a lot of other methods either didn't detect, or so weren't sensitive enough. So some of the learned methods that we tested weren't really sensitive enough to detect these subpixel flows. while other methods usually, if you detected them, resulted also in a lot of noise. And I think Conjunct, because it smooths it a bit over a window or a certain window that we tuned, in the end it performed quite well because we get kind of the best signal to noise ratio out. So we could detect the flows with the minimum noise. As you can see, probably I think here on this page on the bottom right, you can see some example flows. Yeah, here. For example, these are, for example, some small scale or some snapshots. For example, the left, we have the kind of the large heat plate close to the camera, so where it really is kind of almost the whole image kind of contains some Schlieren flow. On the right hand side, it's the same heat source a bit further away from the camera, so you can see kind of there would be some region where we don't have any flow. And on the right hand side, you can see the small heat plate, which usually at the bottom, it had some laminar flow. So that's why you can kind of see just one column going up and not as in the left side, kind of this chaotic behavior of the turbulent flow. And for example, for all these pictures here on the bottom, on the top left, you can see a number. And so this is kind of the maximum flow magnitude. So on the left image, we had a maximum optical flow of 0.4 pixels. And on the right-hand side, we had 0.06 pixels kind of motion. So if we looked at the video, we couldn't really observe any of these flow patterns kind of from the video itself. So, yeah.
Question on the setup of this. Is there a reason why you chose to conduct it indoors? So obviously it's a more controlled environment and that could be good for some cases, but I'm thinking if you had a setup like this and you're looking to generate data in such a way, specifically as to mimic outdoor scenarios where you could have more variation in how the turbulence arises, rather than trying to simulate that in some way, would it make sense potentially to have an outdoor setup that's still somewhat controlled, but where you have the the wind and stuff like that affecting it? Because even if in a setup like this, even if you have fans or something like that to try and direct it or make the environment a bit more turbulent, you're kind of just trying to mimic something that already happens in a pretty good way with varying wind conditions, etc. if you're outdoors.
Yeah. No, I agree. So I think for a better result, I think, and also making it work outdoors. So you might want to reconsider how you generate data overall. So I think doing it outdoors, if you can get high quality data out, so if the POS methods also kind of get good enough results outdoors, I think that would work quite well. I mean, one challenge there that I also observed even in our indoor setting is kind of, it's behind kind of the view we have in this picture. There was also, for example, a window. And for some of the recordings, for example, we started it when there was sun out there, but then there was a kind of a cloud in front of the sun. So the whole kind of illumination changed, which then also meant that kind of this recording in the end we couldn't use because kind of the illumination change by itself already introduced kind of a perceptual motion. So, I mean, the background didn't really move, but kind of just because of the illumination change, kind of the BS method would detect kind of a small scale, constant optical flow that would overshadow kind of these recorded Schlieren flows or kind of these distortions due to the heat source. So kind of it's really hard to detect these small scale optical flows. So, I mean, one solution overall could be that for the data recording, you use a much higher resolution cameras that you potentially couldn't really use on board, but because then you're not talking anymore about subpixel flow, which would make the whole, let's say, data recording much more robust. So this is probably one direction that I would go for. Because, I mean, if you record, for example, with this camera, if you have let's say a 0.1 pixel flow, if you just have 10 times higher resolution, then you would talk about pixel resolution flow. And that would just be much easier kind of to control, and also kind of these small scale effects wouldn't affect the data recording or the quality of the data recording as much.
Okay, so let's talk about the training of the network, and let's keep it to that for now. So you have this setup, and how is that relevant for then the subsequent training?
Yeah. So I mean, with this setup, I mean, this is also kind of the first step that we did to verify whether a neural network can do this, because we didn't start kind of with the full training. We made baby steps towards this. So what we did is, with one setting, we just chose that data. So we have on one hand kind of the input image, and on the other hand, with the back BOS method, we have an associated kind of flow pair. And then we just let the unit structure, let's say, work with that data to train it with a simple L2 loss, and hoped that it would learn these flow patterns, which eventually it did. So it works actually quite well with this one setup. What we then did as well was, okay, so we changed in a bit different setup. So for example, different heat sources, but still with the same background. So this worked as well. But then, I mean, obviously, because the network has only seen one background, when we tested, for example, on any other backgrounds, it would fail doing so because it overfit or it was very specialized for this one background. Then in the next step, what we did is kind of, we had these different background patterns. I think it was checkerboard, Perlin noise, sinusoidal patterns, and also kind of a multi-scale pattern that you can see here on the top right picture. Kind of these are the different backgrounds that we tested. And then you also recorded data on these different backgrounds, and we let the network train as well on these different kind of high texture backgrounds. In this next step, it still learned it, but then again, if we tested on any random background, it still kind of did not work. And this was then when we kind of went away from recording more data, and we kind of introduced this other sample type, so the synthetic samples. And what we have there is we leveraged kind of a large image data set called Places dataset, where you have millions of images from kind of different scenes. So you have houses there, you have, as you can see here on the left. So you have horses, you have natural backgrounds, you have images, you have quite different settings. And then we generated artificial samples with those images. And we did it, we just randomly chose a certain image. And then from our set of recorded optical flows, we also randomly chose one. And then we applied this kind of optical flow pattern as a warp map, which meant that in the end, we have an image consisting, or let's say, including these very small scale distortions. And then we also showed these samples to the network as well. So we have kind of one artificial image containing these flow patterns, and then the associated kind of ground truth flow. And then we let the network to train on this as well. And during training,
sorry to interrupt. For the airflows that you aggregated onto the images here that we're seeing in this figure, are you saying those were from the BOS method? So you ran the BOS method, got an extract, and then, okay. As a follow-up question to that, did you observe, if you're testing it on the actual background versus a background like this, did you see a noticeable difference in attenuation or something like that from your network? I'm thinking because in this application where you're extracting something with BOS first, then putting it in as an overlay onto something else and then trying to extract it again, if you're manipulating the information, because BOS is not perfect, I guess it deals with these situations kind of well, I don't know, but I would suppose so. But then you're overlapping it again. Did you notice any substantial losses in quality in that second piece of data?
I mean, we haven't really compared it in the way that we looked at one sample and compared it, for example, with this random image and with the actual, let's say, data collection image as well. I mean, what we, for example, observed sometimes is that for some of the, let's say, I mean, obviously, I mean, these are all samples that we show here that the network hasn't seen during training. So it hasn't seen, for example, these flow patterns and these background images. But we tested it, for example, for some of the images where the network has seen it during training. And for let's say for these kind of data collection samples, the network obviously works quite well. Sometimes even, for example, surpassing the BOS method in a sense that in some samples, the BOS method exhibited kind of artifacts that correspond or correlate with the background. So, for example, for the checkerboard background, sometimes you could see that there would be kind of these small checkerboard patterns are visible in the predicted output or in the BOS output, whereas our network resulted in a much smoother kind of output prediction or flow prediction because it also has seen other backgrounds and knows, for example, or could infer that kind of this pattern is just due to the background. So this could be filtered out. I mean, in terms of actual performance on these synthetic samples, I mean, we observed much more higher correlation between the actual background and how well it works. Because, for example, you can see kind of in the second image or in the second row, I mean, there we have quite high texture background, so the whole prediction works quite well. And also for the anime picture, which is the third one, and even for the fourth one with the lake, there seems to be enough texture such that the network can detect kind of these distortions. Whereas at the bottom two cases, so for example, with the night sky, which at least is almost, I think in this case, uniformly black, or the sky, which has very small gradients. I mean, arguably there, it's also pretty hard to see if a pixel that looks almost the same as the one next to you shifted by 0.2, or there's a motion by 0.2 pixels between two pixels that almost look the same. So that's usually the cases where it broke down. So it's much more, this is kind of a cause of, or indication of performance, rather than, let's say, if it's close enough to the background that we've seen or anything else. Yeah.
Yes, definitely. So that makes perfect sense. It's kind of different from the concern that I'm trying to get to, though. The concern that I'm trying to get to is if you imagine the approach that you took for generating these samples compared to an alternate approach where you would take one of these images and then you would simply simulate what the airflow would be. That would be another way of generating that data set. And my question is more why we have confidence in the quality of our data set that we get by extracting the airflow with BOS first. Because as you said, with the checkerboard, for example, you do get some artifacts sometimes when you're extracting the airflow with BOS. And the downstream effect of that is you're training your CNN now on data, which is already which already has some bugs in it. Let's put it that way. My question is just: did you observe any noticeable kind of difference in the quality of the images, like of the training images you got after applying BOS? Did you do something to assess that?
No, I didn't do anything. Or I mean, I looked at the prediction, or kind of I did not do a qualitative assessment. So I did some, or I didn't do a quantitative assessment. I did some qualitative assessments, kind of in the end, it looks fine, or that we do not have strong kind of distortions. I mean, some data sets we had to, for example, discard because BOS failed. We just had, for example, something moving very slightly. I mean, the confidence in that data set comes from the fact that, I mean, BOS is quite, let's say, traditional method that has been widely utilized. And we actually were also thinking about, so this was kind of, I didn't have time to go in towards that direction, but I also thought about kind of having a simulation where we have, for example, bubbles going up, and then, for example, simulating kind of captured flows with this setup, which could then also result in a much richer data sets, because we could simulate any background. We could simulate also much more diverse flow patterns. So when here we're a bit limited to the flow patterns that are due to the heat source. So this is kind of maybe one advantage of doing it in a simulation. And one downside that in the end caused us to not go too much towards that direction is that we didn't really know, for example, how to simulate this. So, for example, also we didn't really know how we would model, for example, these kind of temperature gradients in the air. Are they kind of sharp gradients? Are they dreidel gradients? Is it kind of how large are these bubbles? Is it even a bubble? Is it more like, let's say, kind of a chaotic field of kind of gradual changes in density? So this is kind of where we were not really sure how we would model this in a simulation setup. And that's why we chose kind of this approach where we have at least the flow patterns are something that we would observe in the real world, or that are kind of realistic, because the world is the best physics simulator you can get. And at least with the data recording, there are ways to improve it. Or maybe in the futures, if you want to improve this, maybe you have to rethink that. But I think at least, let's say, the observations that you make are some that you can get in the real world. And at least, for example, for different flow patterns, later on as we tested, we could show that it could also generalize to flow patterns that the network has not seen during training. So it's not really that it's sticking only to this phenomena that you can see here in the recorded data sets. So it's really also generalizes to that perspective. So it's really more of an issue that the network at the moment does not generalize to any random backgrounds that we have kind of in the real world.
Mm-hmm.
It's more limitation. Okay.
Thanks for the clarification. I want to move to the results soon. I just want to have a quick look at the training like figure that you included here as well. Would you mind just elaborating on what the two stages of training are? Because we have this distinct kink here, which kind of separates the two regimes. If you would just want to go through the procedure.
Yeah. So I mean, the training actually was also something the network in the end. So with all the data, didn't kind of or train out of the box. We so if we would train it with all the data that we have, usually what would end up happen is that it would only kind of learn our, let's say, data collection samples, so the one with the real background, and not learn these kind of channel backgrounds, because the network is lazy and it's much easier to learn kind of these restricted backgrounds. So it could overfit to just these backgrounds than working on any random background. So what we did is we first had a very limited data set of optical flows and also backgrounds. And we would train with 50% of these realistic backgrounds and 50% of these random backgrounds that are artificial samples. And it still first would be lazy and only learn these, let's say, realistic data collection backgrounds. But then after some point, you can see here about as epoch 350, 80 or something like that. Yes, here. So it would suddenly also learn kind of both samples as well. And then we trained in this first stage the network for 1000 epochs. And this behavior is really something that we observed also over different training runs. So very exactly, this peak would happen, would vary a bit. But the network really always would first kind of overfit or learn these more simplistic patterns or samples before kind of learning to predict both tasks or both background types well. And it's kind of during this training run, at least for this 1000 epochs, we didn't change anything. We didn't modify any learning, or the learning rate was actually decreased every 400 epoch, but kind of where this peak happens didn't correlate with us modifying any hyperparameters in the learning. So I think it was purely just by luck. There was a strong enough gradients pulling it towards learning both. So, and then I think afterwards we did some refinement steps where we then let this pre-trained network learn on the full data sets. So with all the different flow types that we have, with all the different also natural backgrounds that we collected, and then we let it train for another, I think, 1,000 or 2,000 epochs, just to refine and also overfit also to this much richer data set.
Were there any additional actions that you took to prevent overfitting in this case, or did that cut it, the ones that you mentioned now?
Yeah, so these were the ones that we cut. I mean, I think what we really wanted to do within this work, we are aware that there are much more, let's say, sophisticated approach for us, for example, also to avoid overfitting, but we really wanted to go with a minimal approach, because even, let's say, we did some steps, it worked, but then when we got towards the more complex, let's say, use case, it always failed first. So we didn't want to introduce kind of too complex algorithms, because then there was also more parts where it fails. So that's why we kind of, from a machine learning perspective, kind of our approach is pretty standard, or it's even very, let's say, simplistic.
Okay. Is there anything else you want to add on the training procedure before we start looking at the results?
No. Let's have a look at the results.
Okay. Would you mind just elaborating on what the different parts of the validation were? Yeah. So, like, in what different stages did we look at how the model performs?
So we have kind of the first stage is kind of the test data set, where we have kind of held back data. So during the data recording, we had some backgrounds, that we held back, and then we evaluate the network on those. We also have, for example, for these artificial samples, we have some backgrounds that we didn't leverage during training, so we can also evaluate these samples there. And so this is kind of the first step, because this data set is quite similar, although not identical, to the one that we used in training. And then in a second stage, we had some samples where we messed around with the flow. So for example, we used kind of a small plate to deflect the flow. We poured some water on the flow, kind of to result in different flow patterns. And there we could test whether the network could generalize to kind of these different flow patterns that it has never seen before, that are also distinctly different from the ones that we recorded. And then in the last stage, we tested it in an indoor setting with a moving camera to really, so we moved the camera around and saw to evaluate how well does it actually work in the target use case that we intended this method for.
Do we actually have some of the videos that are in this report? Do some of them actually illustrate the results as well, or are these?
So kind of the wind combined one, for example, there you can see the second stage one.
Okay, so let's have a look at this.
Or maybe this is the water one. So for example, here we poured some water. You can see on the left-hand side, you can see kind of the image the image stream, so the video that we record, and on the right-hand side, the kind of the network prediction. And for example, what you can also see is that even though kind of the student, when he moved into the frame and kind of poured the water on, for example, it does not get picked up by the network. So it really learned to kind of reject or to not, to not react to these changes in the background. So for example, any BOS method would struggle kind of to get here some meaningful results, or at least would have very strong artifacts around kind of the border of the person moving in. Maybe if we can go to the other video, the one with the wind, there you can see really also a bit more different, or the one at the bottom. So here you can see also really some distinctly different flow patterns. So initially, I think, yes. So for example, once he starts moving it up and down, you can see kind of the flow reacting a bit due to the wind induced. And our network really can pick this up quite well. And if you go maybe skip a bit further forward, maybe to about 40 seconds or so, I think at some point, so here he holds it, so you can see the flow going around, which is something really the network has never seen during training. So this is kind of really completely new patterns. And now I think in a few seconds, he will start moving the plate up and down. And there you can see, for example, the tip vortices that you would expect kind of forming at the tip of the blade. And even our network can predict kind of these flow patterns quite well. We also, for example, I think in our paper video that we uploaded to YouTube, we also showed kind of the corresponding BOS prediction as well. Which also validates a bit what our networks predict, because if you observe it closely, kind of we can see the same patterns in our network, but obviously the BOS method, it is overshadowed by some artifacts that are due to the plate, due to the person stepping in there. So our network prediction is much, much cleaner than the one.
Do you have a conceptual explanation for why your solution is effective at not taking those things into account? Or maybe that's a poor way of formalizing it. I don't mean that it doesn't take them into account. Rather, it does take them into account and neglects them deliberately in the output, right?
Yeah. So, I mean, the BOS method obviously takes it into account because it has some notion of how the background should look like. And then there's something different there, and then it doesn't really know how to deal with this big obstacle that hasn't been in the image before. I mean, our method really comes from the other perspective. So it assumes just we have some background that can look however, it doesn't have any assumption about the background, and it tries to kind of isolate these patterns that are due to this kind of flows. And I think how exactly it works, we are not really sure. I think in the end, how it analyzes kind of some frequencies that appear, maybe kind of color, maybe illumination in the image, and then it tries to determine whether kind of it matches with what it has previously seen, kind of in terms of these flow patterns. So I think it doesn't have, why it learns to ignore them, it's just it doesn't have any notion of how the background should look like. So it doesn't matter if there's something in the background or not. It's really only interested in kind of the effect that we have due to this kind of thermal up, or due to the density gradients in the air. Yeah.
It would be quite interesting to see how it reacts to something that's moving, like pretty quickly in the frame, because it seems to me like what it's trying to do is capture two like pictures, like two pictures next to each other in terms of frame rate, right? So you have one picture and then one very soon thereafter, and you're kind of mapping them on top of each other, trying to see what the distortion is. And assume you have some object in it that kind of moves, like not because there's a distortion, but because it physically actually moves. I wonder if the model would think that that's corresponding to a distortion as opposed to just physically moving the object.
So I mean, just to clarify, so our network only takes one single input image. So it doesn't have two images. So the network really only has one image, also one frame of the video. So, and based on this one frame, it predicts the flow. So what could be an issue of very fast moving objects is that if you have, for example, would have motion blur at some point, that could potentially maybe look like these distortions. So that could mess up the kind of the prediction or the network as well. So also consequently, for example, if you have then a camera that moves around, if it moves around too fast, it could also, or if you were not getting a sharp image anymore of your background, it could also kind of result in poor network predictions. So this could also be, for example, one reason why you want to have a simulated setup, because then you could kind of potentially simulate all these effects in the end, where you have, for example, moving camera, you have moving objects and how they influence kind of the network prediction. But since our network really has only one single image as an input, kind of as long as the object is sharp, I mean, the network doesn't even know that this single object is moving. So it doesn't matter for the network. So
thanks for clarifying. In terms of the results then, would you mind summarizing? So we talked about the evaluation methods. Would you mind just summarizing the big picture of what the results were for the paper? And then for anyone who's very interested, they can, we'll link the paper so they can look at the figures in detail as well.
Yeah, so I mean, the paper is kind of a neural network-based approach that enables to detect on one single grayscale image kind of these small Schlieren flows, or the optical flow due to the Schlieren. And so far it works quite well on the test data set where we tested it. It also works well in an indoor setting with a static background. When we finally then evaluated it on a moving background, it still performs well, or on this data set where no other method has previously been able to detect optic flow, it works for some viewpoints. Yes, you can see here at the top. So for some viewpoints it worked. For other viewpoints, it still doesn't work. So the network still, in the real world, unfortunately cannot be applied. But at least in essence, kind of it's a next step towards reducing some of the limitations that we had in this line of work for applying it for UAVs. It's not the end solution, but it's kind of really a step towards deploying such algorithms on board UAVs.
My understanding is, in terms of improving this, the key thing that you're listing in the paper is better acquisition of data, or data that's more at least appropriate for the kind of solutions that you're looking to apply this to. Do you have some notion, and you elaborated on a few ways that you can improve this going forward, but do you have a clear take, like as a conclusion, what you think would be a good acquisition strategy for better data if you got to do a new study?
Yeah. I think I would really invest in a kind of much higher resolution camera, because still in our kind of data gathering, it was really hard to get a good kind of signal out with very little noise. And if you had a high resolution camera, you could reduce that. I think as you outlined, potentially, I think doing all of this outdoors might be also interesting because we could see maybe more realistic flow patterns, or I mean, maybe some flow patterns that happen more outside also affected due to the wind. And we also could have illumination changes. We could have also other effects, because I think outside also we might even observe some small patterns, just because there are temperature gradients kind of off the floor, which also result in into temperature gradients in the air, which is indoors just much less likely to happen. So I think doing it outdoors could happen, or even as generating some kind of artificial data with some physics simulator where you could inject some flow patterns and just generate kind of the corresponding expected flow in the image, kind of that could also leverage towards, let's say, detecting kind of different viewpoints. Because I think as the kind of the moving camera shot or experiment showed, kind of, I think the distances where it works well also corresponds a bit to the distance to the background where we recorded data. So obviously, I think we also would need more data with kind of different distances between the background, the heat source, and the camera. And I think in a controlled setting, kind of recording this data set is quite hard, because at least for our data acquisition, we need the BOS method. So at least the distance between the camera and the background needs to be static. Mm-hmm. So we could potentially move the heat plate around. However, it's either you spend a lot of time recording different setups, or you generate a physics simulator where you could really kind of get kind of a continuous distribution of different distances between the heat source, the camera, and the background.
Mm-hmm. Okay, very good. I'm happy with the takeaways from the paper here, so I'm fine to wrap it up. I would just ask, as a final question from my side, if you have any asks from the community or people looking into similar research, either if it's papers in this area where you would like to see additional investigation or something of that sort.
I think, it would be interesting to see a bit more, or cool to see some work into actually subpixel optical flows. FlowNet 2 did some work towards that, but I think other than that, it's also very specific to this example here. But if someone else kind of maybe investigates a bit more how we can, or which network structure actually work best to detect such flow patterns, or also I think for thermal soaring overall, it would be also pretty cool to see a bit more, or some work that actually does this outdoors. As you can see, for our approach, kind of it works indoors. But as soon as you go out to the real world, there are a lot more, or the real world is much more complex. And actually trying to test these algorithms outdoors, that would be pretty cool. Or if someone would pick up this line of work and actually can show that it also works outdoors, that would be pretty cool. So.
Okay, very good. Then thank you very much, Florian, for taking the time. I enjoyed it.
Thank you. Yeah, it was a pleasure talking to you about the paper.